Okay, we essentially finished chapter 4. We had a few slides to go, but we finished talking about really molecular polarity. So we'll just use this to review what we talked about. So remember that when we talk about molecular polarity, we are talking about the overall molecule as a whole and all the bonds that are involved with that molecule, and trying to decide as a whole, is the molecule, is there a side that is more negative? Is there a side that's more positive based on unequal distribution of electrons over the entire molecule? So in order for a molecule to be polar, as we talked about, it does need to technically have polar bonds. And that is, again, bond polarity, where we do use the electronegativity difference. And usually those unsymmetrical shapes. So as we talked about, those bond dipole arrows are vectors. And again, if things end up being sort of equal and opposite of each other, they will sort of cancel each other out. If they're really not sort of equal and opposites of each other, then they will not cancel each other out. So remember, for the most part, symmetrical geometries are geometries where you kind of draw your Lewis structures and you really don't have dots on the central atom, and everything on the outside is pretty much the same. That usually will result in everybody ending up being pretty well equally spread out from each other, and those vectors, if they do have polar bonds, will cancel. The unsymmetrical geometries are the ones where you basically draw your Lewis structures and you have dots on the central atom, and if everything on the outside is the same, then it will be a polar bond or a polar molecule. And that's because, again, you won't have the really symmetrical sort of area where everybody will cancel each other out. So you'll end up having really one side of the molecule kind of pulling more in terms of electrons than the other, and that will result in usually a polar bond. The other thing that we saw is you can have a molecule where you have no non-bonding electrons on the central atom, but if everybody on the outside are maybe some different atoms, that also will typically cause a change in the polarity of it, and it will end up being a polar molecule because of some unequal kind of pulling or of a different element on the outside. Let's see, polarity, molecular polarity means that a guy will have a dipole moment. So a dipole moment is represented by the same arrow that we've used for bond dipoles. And again, of course, points to the more negative side of the molecule in this case. So something like water, again, is a polar molecule because it has polar bonds, and its geometry of bent or V shape allows those guys basically to add to each other, and the oxygen side being more negative, the hydrogen side being more positive. There's kind of a couple of exceptions, though, that you can draw a Lewis structure where you do have dots on the central atom and it will be non-polar, and that is the, again, expanded octet linear, and also the square planar, which is also the expanded octet. Those guys, because basically it is linear, it's got the same guy at both ends, and it's got the non-bonding electrons happening. These guys end up being pulling equally to each other. So even though it does have dots, it will be non-polar in that case. And in the case of square planar, you basically got your square happening with some dots opposite of each other. So again, basically these are all equal and opposites of each other, going to kind of pull or push, and they're going to cancel each other out. So those are two sort of notable exceptions to sort of the quick way of figuring out molecular polarity, where again you can get some dots on the central atom and have everything on the outside being the same, but it will be non-polar in this particular case. Most of the time, if you do see dots and everything on the outside, it's going to be a polar molecule. Non-bonding electrons affect molecular polarity. They do pull the electron density strongly. So again, those non-bonding electrons do have some type of pull on it, and it can affect the polarity of a molecule. Any questions on that there? So here's a couple of examples of some stuff we talked about, I think, as well. We also talked about the idea that really the one place where bond polarity and molecular polarity is really going to be the same is with those diatomic molecules. And again, it's because they really have just one bond, which means if that bond is polar, then the molecule will be polar. And if that bond is non-polar, then the molecule will be non-polar, because simply there's just one bond in there. Remember that when it's 3 or more atoms, you have to look at those two things we just talked about. Are there polar bonds and the molecular geometry to determine if it is going to be a polar or non-polar. And again, CO2 is a good example of that we talked about last time. Once again, although it does have polar bonds, because of its geometry being linear, these guys are again going to pull pretty much equal and opposites of each other, and they're going to cancel each other out. So definitely possible to have something that has a polar bond in it, but overall we'll see sort of equal sharing of electrons as a whole in the entire molecule. And that's what we see here, typically in these sort of electron density diagrams. Red areas are usually areas where there's a lot of electrons, and blue areas are kind of places where there's not so many electrons. So here we got kind of a neutralish sort of color, which indicates, sort of equal distribution of those electrons over the molecule as a whole. And here you can see in water, we have much higher red, sort of like it has a lot more electrons up in that area. And down by where the hydrogens are, again, it's a lot more blue, showing these sort of unequal distribution as we talked about there, and our dipole moment happening there in water towards the oxygen being more electronegative. Same thing here with ammonia. A reminder that, again, we do have these non-bonding electrons. So we do have a net dipole moment heading towards the nitrogen, and overall heading upwards kind of towards those non-bonding electrons as well. Now, molecular polarity, as we'll talk about in a later chapter as well, is really important in terms of how other molecules interact with one another. Pretty much the basis of how all molecules sort of interact with one another is a pretty simple idea of basically electrostatic attraction. So it's basically opposites attract. And that's how, for example, water interacts with water. So water interacts with other molecules. And when we get to things that are basically similar in terms of their polarity, they typically are soluble in each other, which means they mix. And that's why things that are polar and polar are soluble in each other. Things that are ionic and polar are also soluble in each other, because ions have charges and polar things have a positive side and a negative side. So there's an attraction that can happen between them. And one that sometimes people miss is nonpolar things, actually. And nonpolar things are actually soluble in each other as well. And again, because they're using really the same type of forces to interact. You only get in trouble like we see over here when we try to mix polar and nonpolar together. They are insoluble in each other. And that is because, just very simply, oil right here is nonpolar, and basically it's neutral. It has no charge. Water is polar, which has a positive, negative side. So over the long period of time, they do not have a way to interact well with one another. And that's why you typically will see oil kind of floating up there on water. They will mix a little bit, but for a short period of time, they cannot really maintain that interaction. And it's really because the only way that something like oil can interact with water is it has to temporarily become charged. So it's got to temporarily pick up a positive and negative charge. And so for a short period of time, it could do that, but it's going to kind of lose that charge and gain it and lose it. And that's different than water, which no matter what you do to water, it's always got a positive side, always got a negative side. So it's always good to go in terms of interacting. But something like oil, which is nonpolar, or most nonpolar substances, needs something to occur to cause it to temporarily gain a charge. And then they can interact. But again, it's just a very temporary sort of situation. And that's why when you take like salad dressing, right, oil and vinegar, salad dressing, right, mix it up, right, it mixes for a bit. But if you leave it, eventually over a long period of time, will separate out from each other. Because again, they have no way to maintain that interaction over a long period of time. That's soap. Good conversation. Soap is actually two parts. Soap is this part here, which is a bunch of carbons and hydrogens, sometimes in organic chemistry drawn like this, where all those guys are carbons. And there's basically hydrogens attached to all these guys. And at the end here, it has this. So this is what is sometimes referred to as the nonpolar tail of soap. And this is a polar head of soap. And that works really great for soap because most dirt is nonpolar. So the tail of soap basically will be able to interact, drawn by my wiggly line there. And the tail of soap there will be able to interact with the dirt really well and trap it in what's known as a micelle. And when we usually use soap, we usually wash it off with water, which works really well because it aligns itself at the outside of soap, which likes water, hydrophilic, likes water, ends up being on the outside with the dirt trapped on the inside with the nonpolar part of soap. So when you wash yourself with water, out goes the soap that has the dirt trapped and you're clean. Good to know how soap works. Any questions on that there? So again, it does play obviously a lot of roles in different areas here. All right, so let's take a look at these. So there's some electronegativity values. Here's these shapes. Take a second to determine is it polar or non-polar, these molecules. Use these electronegativity values to help us decide if there are polar bonds. So between nitrogen and oxygen, if we subtract it, that's a difference of 0.5, which means it is polar. And if we were to draw the arrows, it would be heading towards the oxygen. Between nitrogen and chlorine, in this case, it actually is 0, the difference, which means it's actually non-polar. It's one of those diagonal relationships on the periodic table. And in this case, it does have polar bonds. The geometry here is 1, 2, 3 electron pairs and 1 and 2 bonds. So that is our good friend angular, right? So overall, this molecule is going to be polar or non-polar. It is going to be polar, yeah. And again, we could quickly do it just looking at it and go, I see dots, and frankly, not too much going on the outside. But basically, it's angled like this, right? And basically, we have this side pulling, right? So you can kind of imagine if we just pull on that side, the whole thing's going to move, and like the kind of rope example, and it would be polar in this case. Over here, we got sulfur and oxygen. Difference is 1, which definitely is a polar bond. So we do have these guys going in this direction. So it has polar bonds. In this case, this guy's going to be, it is going to be non-polar. We could use our quick way of no dots and everything on the outside is the same, and it will cancel each other out. So again, even though it does have polar bonds, this is trigonal planar, right? Which is like a triangle. So you basically got everybody pulling equally, right? And opposite corners of a triangle. So again, they're going to basically cancel each other out. Any questions on that there? All right. And we talked about CO2. So clearly this just illustrates the idea that you do have to take into account the geometry. And as we know, the correct geometry is this guy where they will cancel each other out. Obviously, if for some reason it was bent or V-shaped, they wouldn't. But again, that is not the correct geometry. So definitely has to take into geometry. And it is the molecular geometry you have to take into account when you're dealing with 3 or more atoms. Any questions on molecular polarity to finish it up here? All right, that wraps up chapter 4. We're going to go back to chapter 3 now, I think, and talk about. So this is back to chapter 3. First part of chapter 3 was all the bonding stuff. So the last part here is going to be the naming. So we're going to talk about how to properly name everything, which is nomenclature. And obviously, our naming is going to be broken up into 2 categories, like we talked about with bonding. Ionic compounds, which again is always a metal and a non-metal. And really covalent are molecular sort of compounds where we share electrons. And again, that is our non-metals here together. And really depending on what is involved in these compounds as to sort of how we properly go about naming them. So let us talk about a colorful periodic table there. Not so colorful. But first off, on the periodic table, as you may know, but let's just make sure, there are certain elements that have really fixed charges, right? And that is everybody here in group 1 makes a +1 charge. Everybody in group 2 makes a +2 charge, again, because they are metals, so they lose electrons and become positively charged. Group 3, I would say probably mostly we're talking aluminum there in group 3 is going to be +3. We do have the staircase kind of coming down in this area. So we actually skip group 4 and then back over to group 5 here, 6 and 7. That's going to be -3. And it is the non-metals above the staircase we're talking about. It's going to be -2 for group 6. Again, the non-metals, and -1. So it's kind of like +1, +2, +3, skip, and then go backwards, -3, -2, -1. Transition metals, as you may know, along with these metals down here, which are below the staircase, they can have a variable type charge. So in certain cases, they can be different types of charges. There are 3 exceptions, though, that are transition metals that have fixed charges. And that is this sort of backwards L right about here, where we have zinc and cadmium, then hang a left over there to silver. Zinc and cadmium will always be +2, and silver will always be +1. So those 3 in the transition metal region will have fixed charges. Everybody else, again, will be a variable type of charge that is a metal. Any questions on that there? All right, so when we do have things that are that have charges, those are again are known as ions. And obviously we've talked about it as we talked about bonding as well. We have cations, which are positively charged, and as we talked about, that's usually a result of losing electrons. We also have anions, which are negatively charged, which is a result of gaining electrons. And how we go about naming each of these, if we have the ion by itself, is if it is a positive ion, like we see here on this column, we basically use the whole name of the metal in most cases, except for hydrogen, but in most cases, metal. So that is the hydrogen ion, and the only non-metal there, lithium ion, sodium ion, and potassium ion. If we are to write the formula for the ion, we do need to include the charge. So if we're writing a formula for an individual cation, because it's an ion, you do have to have the charge there. And in this case, you want to make sure that you put it. When we go for our anions here, and again, if we just have the anion, we basically take the non-metal name and we drop the last part, or a little bit more in last part in some cases, and we replace it with the IDE at the end of it. So fluorine becomes fluoride, chlorine becomes chloride, bromine becomes bromide, oxide, and sulfide. Hydrogen is the only element that could kind of go both ways. It could be positive in certain cases, and it can be negative in other cases. Most of the time when you're dealing with hydrogen, it's probably going to be positive. When it comes after a metal, then it will be negative. So for example, if you had something like LiH, this is lithium, which is group 1, which is +1. This, in this case, would be the hydride version of it, where it's -1. And by the way, whenever we put together, as we talked about with bonding, anything that is positively charged and negatively charged in terms of a formula for an ionic compound, it always needs to equal 0, the charge. The overall charge has to equal 0. And that's what we see here. If we take +1 and -1, we put it together, we get just one of each of them, and it gives us an overall charge of 0. If we took something like sodium and oxygen, when we put these together to get to 0, we would need one more sodium in this case, and that will get us Na2O. So when we write the formula for something that is ionic, where it has both the metal and the non-metal together, or the cation and the anion together, we have no charge, but it is still made up of really things that have charges, that are individual ions together. Any questions on that? The purpose of that is, as we talked about with bonding, is that allows everybody to get to the noble gas configuration, right? So the simplest way to get those guys to 0 allows them to reach that noble gas configuration in terms of their bonding. just like our cations here, anything that is a negatively charged guy, and you're just going to write the formula for the anion by itself, does need a charge as well included. Any questions on that there? Okay. So that brings us to type 1 compounds, and type 1 compounds are ionic compounds. They are metals and nonmetals, and pretty much in naming, the most important thing is always the metal. So if the metal's involved, that's really going to tell you how you should name it properly. It's going to determine what steps that you need to do. In a type 1 ionic compound, the metal falls in group 1. 2, 3 are zinc, cadmium, are silver. And once again, what all those guys have in common is they have a fixed positive charge. So no matter what you do to them, they're never going to lose any more than their valence electrons. Like sodium, again, will never lose more than its 1 electron. And again, because of that, if it tries to lose more than it, it's going to drop into its core electrons where too much energy, and it's not going to happen. So sodium will always be 1 electron that it will lose. And when you have that and you can identify the metal as being a fixed charge, you pretty much, that's all you need to know. You could roll right into the naming. So we use the whole name of the metal, and our non-metal gets the IDE treatment. So if we have our CaCl2, when I look at this, I have Ca, which is a metal. I have Cl, which is a non-metal. That automatically tells me I'm an ionic compound. And because I have a metal, that is what I want to look at. And I know calcium is group number 2 on the periodic table, which tells me it has a fixed charge. So that tells me it's a type 1 compound. And that's all the telling I need for this. So I'm going to roll with the whole name here, which is calcium. And the other guy gets the IDE here, and that would be calcium chloride. And again, in this case, it is calcium chloride. There is no dichloride or anything like that. There is no prefix. You could have 400 of these here. It will not affect the name. So again, people always want to put extra sort of prefixes on these things. This is not a place to use prefixes. So you do not use prefixes for sure with any ionic compounds. And if you find yourself doing that, you should just put an X on it yourself. Yes, because it definitely will be wrong. Again, this is the formula that we get for calcium chloride is CaCl2, because again, calcium has a +2 charge. Each of the chlorine is -1. And the 2 means that we have 2 of these. It does not mean that the anion is this. That is not the anion. This is the anion formula, and that is our cation formula. So if I had something like Na2S, this should be called not everybody at once. This is sodium sulfide. So once again, if we look at this, we got sodium, which is a metal, sulfur, which is a non-metal. So again, tells us it's ionic. We look at our sodium here, which is group 1, tells us it has a fixed charge, which is type 1, and that's all we need. We're going to go with sodium and then give the IDE treatment there to sulfur, and we end up with sodium sulfide. Once again, here the 2 has no effect on the name either, so you should not use a prefix even on the first name either. And again, the 2 is there because the cation in this case is a sodium with a +1 charge. Again, not Na2+ or anything like that. Anion is sulfide there with a -2 charge. So that is why the 2 is there, to show that we have 2 of those ions in that particular case. Any questions on that there? So here again, it's our chart of our fixed charges, along with again our zinc, which is +2, our cadmium, which is +2, and our silver, which is +1. By the way, if we have any of these elements by themselves, do they have charges? They do not. So things only get charges really when metals and non-metals hook up together, like we talked about with ionic bonding. So they don't have charges really until they kind of hook together with either a metal or a non-metal. All right, so why don't you try some of these here, and why don't we do some names to formula? So why don't you write the formula for, let's do lithium nitride. Let's do aluminum oxide. Let's do barium Okay, let's take a look and see. So once again, the best thing to do is really try to identify what you're dealing with. So here we have potassium, which is a metal, Cl, which is chlorine, which is a non-metal. So once again, I do know I'm dealing with an ionic compound. And whenever I have a metal involved, that is, again, the most important thing. So potassium is group number 1, which tells us it's a type 1 compound. It has a fixed positive 1 charge. So really what we're dealing with here is our cation is +1 for the potassium. Our anion is -1 there for the chlorine, our chloride. And really that's all we need to know for this. We're going to use the whole name here of the metal, which is potassium. And again, our non-metal will get the IDE treatment at the end there, which would be potassium chloride. Any questions on that one there? Taking a look at the next one, Zn is zinc, which is a metal. S is sulfur, which is a non-metal. So once again, that's ionic. Zinc is actually a transition metal, but it is one of those 3 that have a fixed positive charge. So it is named like a type 1 compound, and that means that zinc always has a +2 charge, and that matches really nicely here with our sulfide that has a -2 charge, which is why the formula is ZnS, just one of each to get to 0. Once again, because it has a fixed charge, just need to use the whole name of the metal, which is zinc, and again, the IDE there for our sulfur. Looking at the next one, which is calcium, which is a metal, bromine, which is a non-metal. And once again here, calcium being group number 2 has a fixed charge, and that is going to be calcium with a +2 charge because it is group 2. And this is group 7. So once again, the correct formula for the anion is just Br-. So again, people always want to go like Br2 on the bottom. The 2 again means that we have 2 of those -1 charges, again, to balance out the +2 charge to get us to 0. But again, it is the metal that is most important here. Because it has a fixed charge, we're going to use the whole name of the metal, which is calcium. And the back end there is going to be bromide. Once again, the 2 here has no effect on the actual naming of the compound. Any questions on those there? Lastly, we have barium, which is group 2, which is a metal, and we have hydrogen, which is really a non-metal. And again, in this case, barium, which is group 2, means it's got a fixed +2 charge. In this case, this is hydrogen. It comes after a metal, which means this is actually the negative version of hydrogen, which is H-. And there are 2 of them, again, to balance out the charge. So here we will again use the whole name of the metal, which is barium. And for our hydrogen, it will get the hydride version of its name. Any questions on any of those names there? So those are all type 1. Again, metal always pretty much determines how you should name it whenever you got a metal involved. Now, when we are going from name back to formula, again, if we can determine it's ionic, it needs to equal 0. And we can, in this case, hopefully, lithium a metal. Nitride is nitrogen on the periodic table, which is a non-metal, so we know it's ionic. So what we want to think about is the 2 basic ions that make up each of these. So we know that lithium is group 1, so it has a +1 charge. We know nitrogen is group 5, which means it has a -3 charge. Once again, here the goal is to get to 0. So we do need more of the lithium, right? So we really need 3 total of those guys. to balance out the -3 charge there. And frankly, then you just write what you did there. That's 1, 2, 3 lithiums. All right. And that's 1 nitrogen. So there is the formula right about there. Yeah. Any questions on that one there? Aluminum is a metal, and oxide or oxygen is a non-metal. So again, we know it's ionic. Aluminum is group 3, which means it has a fixed +3 charge. Oxygen is group 6, which means it has a -2 charge. So once again, here we want to get to 0. Easy way to do that is just multiply the numbers together. That's a 6, I think. So to get aluminum to 6, we need not 1, but 2 of them. And to get oxygen to 6, we need 3 of them. And again, you could just write what you did there. So that is 2 aluminums and 1, 2, and 3 oxygens, right? So there we go. Any questions on that there? Lastly, here we have barium, which is a metal, chloride, which is a non-metal, and barium being group 2 has a fixed +2 charge. Chloride being group 7 has a -1 charge. So once again, to get to 0, we actually need 2 of those guys, and that would give us a formula BaCl2. Yeah. Any questions on type 1 compounds, how to name or how to write the formulas? Now, again, I would caution you that sometimes people are taught to move charges down and stuff and move things up to quickly do it. And that works like 94% of the time. So if you're good with 94% of the time, you can blindly just move the charges. It will not work in all cases. So it's best to think about it as balancing out to 0 so you always get the right formula. There's a lot of examples where if you just blindly kind of move the charges up or move the charges down, you will end up with the wrong formula or the wrong name if you do it that way. So keep that in mind. I know a lot of times people are taught that, just kind of swap it backwards. And again, it works 94% of the time, probably. All right, then let's talk about type 2 compounds, which are also ionic compounds, also contain a metal and a non-metal. And once again, here it is going to be our metal that really is the most important thing when we do this. Our metal in this case is going to be a transition metal. Are just to the right on the periodic table, below the staircase. And that's the area where you see things like lead and tin and that area of the periodic table. So remember, underneath the staircase, those are metals, right? Above the staircase, they're non-metals. On the staircase, they're metalloids, right? So we have some metals that fall below the staircase that are technically not transition metals. Bismuth as well, antimony, all those kind of guys over there in that area. They can have a variable type of positive charge. So they're named the same way as our transition metals. Obviously, the 3 transition metals that do not fall into this group here are the 3 that we saw for type 1, which is our zinc, cadmium, and our silver. The deal is here, because they can make multiple charges, we do have to kind of let people know what we're dealing with. So for example, something like copper, I said it right, I would say carbon for some reason. Copper can make a +1 charge. In some cases, copper can make a +2 charge. Iron, for example, could do +2. Iron could do +3. So the additional thing that we need to do when we name these guys is it's very similar to type 1, other than we have to tell people what the charge is on the ion. And we will use still the whole name of the metal. We will still do the non-metal that ends in the IDE to replace the last part. The difference that we do is in the middle there, we're going to use a Roman numeral. And the Roman numeral is the positive charge on one of the metal cations. So very commonly people mistake what the Roman numeral means. Sometimes people think the Roman numeral means how many metals you have. It's not how many metals you have or anything like that. It is if you took one of those metals by itself, what the positive charge is. So you do have to sort of figure out what the positive charge is on the metal. The good news is in these situations, you will always know the charge on whatever it's bound to. So whatever it's attached to, you will know the charge. So you could kind of work your way backwards. So for example, if we had FeCl2, in this case, we would do the same sort of approach. That is a metal iron. That is a non-metal. So once again, I know it's ionic. When I look at my metal, I see it's in the transition metal region, which tells me it probably has got a variable type charge. So that tells me it's type 2. And it also tells me I need to figure out the charge on it. And to figure out the charge on it, you can just simply do a quick math little deal. We do know that chlorine is group number 2. Group number 7 would be better. Group number 7, it's got a -1 charge, and there are 2 of them, which gives us a grand total of -2. And once again, it does have to equal 0. Since there's only one iron, that means that the iron does need to carry a +2 charge in this case. And that means that when we go to name this is iron Roman numeral 2 because of the charge on the metal. And the Cl- gets the chloride just like before. The 2 has no effect on the actual name. Any questions on that one there? Now, the reason we need to use the Roman numeral is because if we had something like FeCl3, once again, we would have an iron that has a variable charge, but in this case, we have not 1, not 2, but 3 of those Cl minuses, which would give us a -3 charge. So in this particular case, the iron's actually carrying a +3 charge to balance it out. And the name of this guy would be iron Roman numeral 1, 2, 3. And once again, chloride, regardless of how many there are in terms of that. So really the naming is all about telling people, in this case, we're using iron with a +2 charge. And in this case, it's iron with a +3 charge. Any questions on that there? All right, so what would be? Here's our variable charges. What would Roman numeral? It should be Roman numeral 4 oxide, not lead 2 oxide, which you would get if you just blindly did that move right there. Yes, and you would get the wrong answer. It is lead 4 because when we look at lead, again, although it is not a transition metal, it's over here below that staircase where they can basically have variable type charges. We do know oxygen is actually group number 6, which means it has a -2 charge, and there's 2 of them, which gives us a grand total of -4. So in this case, lead has to carry the +4 charge in this particular case. So again, as I mentioned earlier, try not to go blindly, just moving the numbers. Again, in a lot of cases, you'll be okay, but there are definitely cases where it will not give you the right answer at the end of it. Question on that one there. Also, one that gets people sometimes is this friend right here. That's mercury. So this is mercury. This is mercury. And oddly enough, the one with all the 2s is mercury 1. Yes, so that is mercury 1. And the one with only 1 2 is mercury 2. And that is because mercury is a dimer, basically 2 +1s together. So there's 2 mercuries together. And that's why there's a 2 on the bottom. And that 2 does stay when you see it in a formula. So that's a real indication of how you know it's like the 1 or the 2. So for example, if we had something like Hg2O and HgO, yes. Here, this is mercury, but it has that extra 2, and we know it has to carry a +2 charge to balance it out. But because of that extra 2, we know it's actually mercury 1 oxide in this case. Here, this is, again, mercury with no 2 on the bottom, but we have the same oxygen, which means in this case it is +2, and that would be mercury 2. So that extra 2 with the mercury 1 still sort of hangs out in the formula, and that's sort of how you could determine that it's mercury 1 versus mercury 2. Any questions on mercury there? You have a much nicer table, I think, than what happened to whatever this table ended up being. So I think what this table is, which I think is on your notes much better than this, but It shows there is an older way that sometimes people will name metals that can have a variable type charge. For example, ick or us is typically how the older names end. Ick is usually the larger positive charge. And OUS is the smaller positive charge. So like iron 3 versus iron 2. Iron 2 would be ferrous, and this would be ferric. Same thing if you had copper 2 and copper 1, that would be cupric and cuprous. And again, you could also see they use kind of the old school type names for those guys. We will not use that in here in most chemistry classes. You don't usually use it too much. Most people use the Roman numerals. So we will use the Roman numeral version of naming these type 2 compounds. And that's what you should use. I will say, though, these couple here or 4 here are ones that do pop up still in like papers, and people use it sometimes in experiments and stuff like that. But for us, strictly for type 2, we will roll with the Roman numerals, and that is the way you should name this. Any questions on that there? All right. Sorry about the spacing on that. I'm not really sure what happened there. All right. So why don't you give these guys names here, and then why don't you also write the formulas for, let's go with nickel 4, nickel 4 sulfide. Let's do chromium 2 oxide. Let's do iron 3 how do we do that one? Let's do iron 3 let's do phosphide. All right, so okay, let's take a look, see how you're doing. So we'll start here. Cobalt is a metal, Cl is a non-metal. So again, we know it's ionic. It is the metal, again, that's most important. And we do see cobalt kind of dead center there in the transition metal region. So that's going to tell us that it's got a variable type charge. We do know that Cl is group 7, and there are 3 of them, which means each one's -1. So that is going to give us a -3 overall. And that means to balance it out to 0, our 1 cobalt has to have a +3 charge. And then we will use the whole name here of our metal, which is cobalt. We will use a Roman numeral 3 for the +3 charge. And once again, regardless that there are 3 of the chlorides, it is just chloride at the end. So this will be cobalt 3 chloride. Question on that one there. Looking here, our friend copper, which is a transition metal, and I, which is a non-metal. So once again, that tells us it's ionic. Our copper also in the transition metal region, meaning that it can have a variable charge. We do know for sure that iodide, that there is group 7 has a -1 charge. So in this case, to balance it out, we just simply need a +1 for our copper. And we will use the whole name here. So that's going to be copper Roman numeral 1. And again, it's going to be iodide here. Yes. Lastly, here on the left, we got SN, which is 10. And that is a metal. We have Br, which is bromine, which is a non-metal. So that's ionic. Tin, again, is one of those ones that is technically not a transition metal, but it is to the right there. That's named the same way and can have a variable charge. So in this case, we do know that Br is -1. And based on the formula there are 4 of them, which gives us a -4 charge. So that's going to be a +4 charge. And that means that this is tin Roman numeral 4 for the charge. And once again, just bromide at the end of it there. Any questions on any of those names there? Working backwards from the name to the formula here is pretty straightforward. Nickel with a Roman numeral 4 means that I have a nickel with a +4 charge. So again, that is what the Roman numeral means. Sulfide is sulfur on the periodic table, which is group 6 there, and that means that it does have a -2 charge. So once again, to put these together, we basically need to get our guy over here to 4, so we need 2 of them, and that will give us NiS2 in this case as the proper formula. Any questions on that one there? Chromium, Roman numeral 2, it looks like I chose there. That's an interesting choice. +2. And our oxide, which is group 6, is -2. So in this case, CrO is what we would need, just one of each. Lastly here, iron 3. That's an iron with a +3 charge. And phosphide is group 5 on the periodic table, which is a -3. So in this case as well, we just need one of each there to balance it out. Any questions on type 2, naming our formulas here? Yeah. Obviously, you need to be able to go both ways. Yeah. Once again, here with type 2, metal, non-metal, ionic, no prefixes. Yeah, so no prefixes at all. So you should not find yourself Roman numering and prefixing at the same time, because again, it's going to be probably incorrect. All right, so here's sort of a decision tree in case you're not sure, but again, it is that metal that helps you determine it, whether or not really the choice here is, do you need or do you not need a Roman numeral? And again, that metal helps you decide that. The next thing we're going to talk about is polyatomic ions, and polyatomic ions are actually groups of nonmetals together that actually have a charge. So if we took something like NH4NO3 in this case, this is actually 2 different polyatomic ions together. We would break it apart right about there. And this is a nitrogen and 4 hydrogens that has a +1 charge. And this guy here is a nitrogen and 3 oxygens that has a -1 charge. So these are still ions, which means when we put them together, we want to equal 0. And that is why we have one of each of these, because this +1 and -1. This is actually things that are covalently bonding and sharing of electrons, but end up with a charge. We might have drew both of these when we were talking about Lewis structures. If you draw the Lewis structure, that is this guy. And if you draw the Lewis structure for this guy, that is this guy. And once again, negative and positive. So polyatomic ions are interesting because they are groups of nonmetals. They really are held together by sharing of electrons. And that's why they will never break apart into like all the individual elements, because they will move around as a group and they will stay connected as a group because they're really together sharing electrons, but they happen to again be carrying sort of an overall -1 charge. Again, we could figure that out by like our formal charge, right? If we did our formal charge, that's a -1, that's a -1. That's a, that is, I always want to put a plus there. That is a 0 here. And our nitrogen in this case is 5 minus 0 minus a half of 8, which is 4. That's a +1, yeah. So those cancel, leaves us with the -1 overall charge, right? So if you calculate that formal charge on each of these. The good news is each of these do have, or the bad news is each of these do have special names. This is the ammonium ion. And this is the nitrate ion. Whenever you have a polyatomic ion involved, you just use the name. So it doesn't matter how many you have of them. It is just the name of the polyatomic ion. So this guy together, when we put it together, is known as ammonium nitrate. Yeah, so that would be ammonium nitrate would be the name of it. I will say probably the ammonium ion is one of the few positive polyatomic ions that you'll see. There's a couple of others like hydronium and so forth. But 9 times out of 10, even maybe a little bit more than that, most of the time your polyatomic ion will be negative, which means in most cases what you're going to have happen is you're going to end up with a metal and a polyatomic ion sort of together. And what essentially happens in this case is because the metal's involved, as we talked about earlier, it is really the most important thing in terms of how you name it. We pretty much will fall back to our type 1, our type 2 naming, which means either the metal needs a Roman numeral or the metal does not need a Roman numeral. So for example, here, if we had something like NaNO3, Na is sodium, and that is nitrate. And again, that is sodium with a +1 charge, nitrate with a -1 charge. So one of each of those guys. The sodium, which is the metal, is the most important thing. Again, it is group 1, which means it has a +1 charge. It is a type 1 metal, which means we would just call this sodium nitrate. Yeah. Now, if we put in there, here maybe, we go with something like this, for example. We'll use our nitrate here. When we look at this particular one, we see iron, which is a metal. We still see nitrate, which is our polyatomic ion. In this case, the iron is a transition metal, which tells us it's type 2. It could have a variable positive charge. So our iron, maybe we're not sure what it is, but we do know that nitrate is a -1 charge, and there are 2 of them, which again gives us -1, -2. That means in this case, our iron has to be +2 to balance it out. And this would be iron Roman numeral 2 for the charge. And again, just nitrate at the end. So I will say probably most of the time it's going to be a metal and a polyatomic ion coming together. And again, you basically just fall back to the metal rules there of type 1, type 2, Roman numeral or not Roman numeral. First off, any questions on that? Why did I lay up a parentheses there rather than just writing the formula like this? Writing the formula like this means that I have 32 oxygens, right, and 1 nitrogen, which is clearly not what's going on here. So whenever you have more than 1 polyatomic ion, you do need to put parentheses around it and the number that you have on the bottom to indicate that you have 2 of those units, rather than in that first case there are 32 oxygens, which you don't. As you can see here, you have basically 2 nitrogens and 6 oxygens in that case, which is what you get when you distribute that 2 in, right, to both of those guys. Any questions on that there? So this is a table of polyatomic ions. I think so. And, the best thing you could do is, memorize it. Yeah, so you do need to memorize the polyatomic ions and their names. And there is sort of ways that you can sort of figure it out. So for example, if we look at something like NO3 minus, as we saw, that is nitrate ion, ATE. NO2 minus is nitrite, ITE. SO4 2 minus is sulfate, ATE. SO3 2 minus is sulfite. The only difference between this guy and this guy is the number of oxygens, right? And nitrate, ATE, has more oxygens than ite. Same thing here. The only difference between these 2 guys is the number of oxygens. They both have a -2 charge. The one that has the more oxygens ends in ate. The one with the least number of oxygens ends in ite. So you could think like you ate too much, right? So that's the one with the most oxygens. So in a group of 2 that are related to each other, the one with the most oxygens will end in ate. The one with the least number of oxygens will end in ite. So sometimes, a good way to do it is just to remember all the eights and know if you need the ites, it's just one oxygen less, right? Or vice versa, you can remember all the ites, and if you need the eights, you just add an oxygen. Everything else will be the same. There are also groups of 4 that are related to each other in terms of polyatomic ions. So something like ClO4 minus, ClO3 minus, ClO2 minus, ClO minus. So if we break this apart here, right about there, each of these guys have a -1 charge. Really, the only difference between all of them is the number of oxygens that are involved. These guys on the right-hand side have the least number of oxygens. These guys have the most. So obviously we know the guys on the right should end in ite as they have the least number. So this would be chlorite. And this guy here would be chlorite. They both can obviously have the same name, right, for 2 different things. So when you have a group of 4 that's related to each other, the one with the least number of oxygens in that group of 4 also starts with hypo. So hypochlorite is the one with the least number of oxygens. Chlorite would be the one with the next smallest number of oxygens. Now, these guys with the most oxygens on the left should end in ate. So this would be chlorate. This also would be chlorate. And once again, we can't obviously have the same name for those 2 different things. So the one with the most oxygens would start with per. So that is perchlorate, chlorate, chlorite, and hypochlorite in that case. These are halogens, which means you could swap out the halogen from any halogen. So as you can see on the list there, if you had BrO3 minus, instead of chlorate, this would be bromate. Yeah. If you had IO3 minus, it would be iodate. Yes. And so forth. So you could really swap out any of the halogens in that kind of group of 4, and they're basically all named the same way. Other things that you'll see on this table is sometimes we will put hydrogen in front of something, or H plus really. So if you had something like CO3 minus, that is carbonate. And if I add an H plus to that, so if I kind of add an H plus, that becomes HCO3 minus. I added the H, +1 and -2 leaves me a -1 overall in the charge. I basically put hydrogen in front of it. So this is known as hydrogen carbonate. And this is also a historical one that people for a lot of years never used hydrogen. They used bi instead. So this is also referred to as bicarbonate, right? In case you have heartburn right about now. And sulfate as well, you put H in front of it. It is hydrogen sulfate, and also known as bisulfate is very commonly still called that as well. If you put 2 hydrogens, you got, come back here, there you go, a little dihydrogen phosphate that occurs as well. Now, I said earlier that we don't use prefixes and like Roman numerals and metals. This would be the only place that you would happen to have a Roman numeral and a prefix together, and that's because the prefix is part of the name of the polyatomic ion, like dihydrogen, is part of the name, or dichromate is part of the name. So that would be the only place where you would get a prefix and a Roman numeral together, and you're really not putting the prefix on yourself as part of the name of the polyatomic ion. Not all polyatomic ions end in H or ite. There are ones that end in IDE, like OH minus, right? That is hydroxide. CN minus is cyanide, IDE. So sometimes those guys do come into play with those in terms of the names here. We have phosphite, we have phosphate, right? Now, you could really apply your group of 4, if you're not really sure of anything. Like, for example, here, we'll do... we have on that list MnO4 minus, right? And that is permanganate. what would MnO4 minus be? I'm sorry, MnO3 minus be. That would be manganate, right? What would MnO2 minus be? Manganite, right? And MnO minus would be hypomanganite, yeah? So this is what I was saying about, learning one of them and just knowing, okay, if I need to kind of go up an oxygen or down an oxygen, how the name sort of changes and what happens. Again, the charge doesn't change, right? So just the number of oxygens change. So that's how you could kind of remember these easier, to try to break it up a little bit easier. Again, pick maybe, the ites or the eights, and you could adjust up or down, depending on what you might need to do or what you see in a particular thing. Any questions on that there? So let's take a look at some here. Let's do, we'll come back here so we actually have the slide with the names here. We'll erase them all. We'll make it maybe a little bit bigger. All right, let's try FeCO3. Let's do MgOH2. Let's do K2Cr2O7. So what are the names of those guys? And why don't you write the formula for, let's do calcium bromate. And let's do copper 1. I'll do copper 1. Something. Let's do copper 1 sulfate. And let's do ammonium sulfide. All right. So give the names for the guys on here. So again, we want to take approach. We see a metal, so that's going to be important. We also see a polyatomic ion. That metal is a transition metal, so that tells us it's a type 2 metal, so we need to figure out the charge. We will look to what it's attached to, which is carbonate in this case. So carbonate here has a -2 charge, which means that our iron here has to have a +2 charge, and this would be iron Roman numeral 2 because of the metal. And we use again the whole name here of our polyatomic ion, which is carbonate. Any questions on that one there? Looking at this, again, we see a metal, which is important. We see again a polyatomic ion. In this case, it doesn't really matter about the metal because it's a type 1, which means we don't have to worry about really naming the charge. So we could just use the whole name, which is magnesium. And again, we'll use the whole name there of our polyatomic ion. And it has no effect, again, that we have 2 of them. The reason we have 2 of them, obviously, here is because magnesium is +2, it's group 2. And each of the hydroxides are -1, right? So that balances out the charge between the 2 of them in this particular case. Any questions on that name there? Coming in here, we see potassium, which is a metal. We see this guy, which is down here, which is dichromate. And once again, potassium is a type 1 metal, which means it is a fixed positive charge. So in terms of naming, that's all I need to know about it, which is potassium. And again, the whole name here of our polyatomic ion, which would be dichromate. And once again, we have the 2 potassiums here because they're each +1. And our dichromate carries a -2 charge. So everything balances out in terms of the formula. Any questions on any of the names there? Going from the name to the formula, we're just going to take the basic units here, put it together properly. So calcium is group 2, has a +2 charge. Bromate is BrO3 minus. So in this case, we have a -1 and a +2. So to balance it out, we need 1 more of these bromates. That means that our formula here would be Ca. We will need parentheses because we have more than one of the polyatomic ions, and we would put a parentheses and our 2 at the end. Any questions on that one there? This is copper Roman numeral 1, so I'll go up on top here. So that means copper has a +1 charge. Sulfate is SO4 2 minus. So we're basically putting a -2 together with a +1. So we do need one more of the +1s in this case, and that would give us Cu2SO4 as our formula. When you have just one of the polyatomic ions, you do not need the parentheses. Yeah, so you don't have to put the parentheses on it. Any questions on that one? Lastly, here we have ammonium, which is this guy right here, NH4 plus. So I'll write it right there. And we have sulfide. Sulfide is basically sulfur off the periodic table. That guy is sulfide, which is group number 6. So in this case, we actually need one more of the ammonium to balance out the charge to 2. And since that is a polyatomic ion, we do need to put parentheses around it and the 2, and then just an S, which is what we need there. Any questions on polyatomic ions? Again, as you can see, pretty much going to fall back to type 1, type 2 in terms of the naming. Again, the metal pretty much determining how to go about naming it. Any questions on naming so far? All right, we'll lay it up there for today.